if you think about it, it's a hard thing to do. How do you measure gravity in a lab? We're talking about you got to be planet sized in order to really feel gravity, right? Like when my mass walks by somebody else's mass, I don't feel anything. Uh, how are we going to measure this? So it took about 100 years for Henry Cavendish to design an experiment, something like this one. We've got largish masses and a couple small ones that are gravitationally attracted to the large ones. Those small ones are mounted on a quartz fiber that's going to twist as the small masses are attracted. That twist is going to rotate a mirror, which will deflect a laser beam just enough that we can detect it. The accepted value for the universal gravitational constant is 6.67 times 10 to the negative 11th. And that times 10 to the negative 11, that's the problem. That's why we needed this crazy apparatus with a laser and a deflection angle, because we can't, with normal laboratory sized masses, we're not going to be able to measure this. Capital G is so small. We would never be able to detect any forces unless we constructed a really sort of sensitive apparatus like this one. Once we have Cavendish's experiment, if we take some measurements for the radius and the mass of the Earth, let's ask about the Newton's second law interaction of dropping an object. The sum of the forces should be the mass times the acceleration. The only force is gravity down. So so let's see the mass of the marker, M. I'm just gonna, you know what? It doesn't have to be a marker, it could just be an object. Oh, the gravitational force between that object and the Earth is let's see, so we've got capital G, the mass of the object, the mass of the Earth, and the distance from the thing to the Earth. Now, where is the Earth? Right? Like if compared to the marker, it's a lot of places, right? It's big. So we need one place that we can represent as the location of the Earth, and the one that we've kind of used before is the center of mass. Which, if we assume that the Earth is basically a sphere and basically symmetric, we're talking about the radius of the Earth is essentially where, because yeah, I'm on the second floor and it's about a meter off the floor, but compared to 6 million meters, the extra, I don't know, 7 meters to sea level isn't going to show up in our calculation. So essentially what we're talking about is the radius of the Earth. And that's all equal to the mass of the object times the acceleration, because gravity is the only force acting. So this mass of the object we can cancel. And Newton's law of gravitation is about to tell us what is the value that we can expect for the acceleration of this object. Oh, my calculator. And those of us playing along at home, I strongly encourage you to actually perform this calculation. It's a really fun thing to see happen. 6.67 times 10 to the negative 11 times the mass of Earth, 5.97 times 10 to the 24 divided by, oops, I'm sorry, I forgot a square. The radius of the Earth, 6.37 times 10 to the 6 squared. This was huge. This was huge. The fact that this law of gravitation that does a good job of describing the motion of celestial bodies and astronomy does an equally good job of predicting and sort of putting in a theoretical context the empirical acceleration of objects falling on Earth. It blew everybody's minds. 9.81 is the numerical answer. It's meters per second squared only if we can agree what the units are for capital G. And the units for capital G are what they need to be so that the result is newtons. So we've got kilograms per meters squared. All right, so it's got to be something with some meters squared. So when we divide by meters squared, they're gone. Then we've got to have kilograms squared in the denominator so that when we multiply by two masses, those are gone. And we've got to have newtons so that we can actually have newtons when we're done. If we use those units for G, the units are going to come out to meters per second squared. And we've got a theoretical justification for our empirical acceleration due to gravity. And again, the synthesis of the astronomical and the terrestrial, was a big, big deal. Big deal. Cool. All right, next segment.